One of the most beautiful things about action physics is how we can understand the origin of conservation laws. We can use the Euler-Lagrange equations to do that. So I'll write it down for a general coordinate. What if this term, the rate of change of the Lagrangian with respect to the coordinate, is equal to 0? Then, now if that's true, the partial derivative of the Lagrangian with respect to the coordinate velocity is a constant in time. That means it's conserved, and as you know, conserved quantities are really important in physics. These derivatives have a special name. The derivative of the Lagrangian with respect to a coordinate velocity is called the canonical momentum associated with that coordinate, denoted by p with a subscript q for the coordinate. Now the assumption we made was that the Lagrangian's derivative with respect to the coordinate was equal to 0. The way that happens is that the Lagrangian simply doesn't depend on that coordinate. The simplest example is a free particle. In 3 dimensions, the Lagrangian is just the kinetic energy, and I'll use Cartesian coordinates. And you'll notice that Lagrangian doesn't depend on the coordinates. It does depend on the coordinate velocities, but not on the coordinates. Consequently, all the canonical momenta associated with those Cartesian coordinates should be conserved. Let's check. What are they? That derivative is just mx dot, or m times the velocity in the x direction, which is our familiar Newtonian component of the momentum. So that makes perfect sense, and you can see that it follows for the other coordinates as well. As we know, for a free particle with no potential, the momentum is conserved, and we now see why that is in terms of the Euler-Lagrange equations. This independence of the Lagrangian from the coordinate is a form of symmetry. If you recall, the symmetry is a transformation which doesn't change something. A free particle is not changed by moving it from one place in space to another. It's not changed because the Lagrangian is exactly the same. So it's the symmetry of the Lagrangian under translation, or its translation invariance symmetry, which gives rise to conservation of momentum. Let's look at another example. A particle constrained to travel in a circle. A bit like the bead on a hoop, but the hoop isn't rotating and there's no gravity. So in that case, the Lagrangian is just due to the kinetic energy, where theta is the angular coordinate. And again, you see that there's no dependence on theta, and consequently the canonical momentum associated with the theta coordinate should be conserved, or is conserved. What is it? And we can rewrite that, recognizing that r theta dot is just the tangential velocity. And that is exactly the angular momentum associated with the particle constrained to travel in a circle. Because the Lagrangian is independent of theta, the canonical momentum, which in this case is the angular momentum, is conserved. The symmetry in this case is that when you rotate the system, it doesn't change, because the Lagrangian is independent of what angle it is at, independent of theta. So invariance under rotation gives rise to angular momentum conservation. Coordinates like the ones we've been talking about, which the Lagrangian does not depend on, are called cyclic or ignorable coordinates. So cyclic or ignorable coordinates are special ones whose associated canonical momentum is conserved in time. Now, this is an example of a much more general result due to Emmy-Noether, which says that for any continuous symmetry of the Lagrangian, there is a conserved quantity. Cyclic coordinates are a simple case of a continuous symmetry of the Lagrangian.